let's look at a couple of the other common sensors, even though they're not ones that are currently being used in your HAP kit. The first one is an optical encoder. The way that an optical encoder works is as follows. You have a focused beam of light, so here's a beam of light, in this case coming from usually an infrared LED, which is aimed at a matched photodetector, which is on this side. And this disc, which we're looking at, this is a side view of the disc here, so I'll specify that. That's a side view of this disc, which is shown over here. And because there are all of these little patterns on the disc, that is, wherever you see a white patch right there, the light can shine through. The LED is going to make a connection with the photodetector whenever one of these white patches is in front of it. And what this does is on the photodetector produces a number of pulses, a certain number of pulses per revolution. And so you can get discs that are very high resolution that have, say, 500 of these little slits all the way around the perimeter. And the only thing to point out with optical encoders in terms of cost is that lots of pulses typically equals high cost, because then you have to have very precision drawing or manufacturing of the slits on the disc. One thing to be concerned about with optical encoders is that there can be quantization problems at low speeds, because if the disc is moving very, very slowly, it's only very rarely that you're going to see a jump in there being a slit to there not being a slit. And so we'll look at this in more detail in the next slide. The other thing to point out is that there are absolute encoders versus referential encoders. And most encoders that people use, the more common ones, are referential. And the idea here is that all that this photodetector can do is count the number of slits that it sees. It doesn't necessarily know where on the disc it is, it just knows how far the disc has rotated, and that makes it referential. But there are some very interesting other types of encoder designs which do not look like this, that provide you absolute position information rather than just a reference position information. So this can let us know a little bit more detail about how the optical encoder works. This is called a phase quadrature encoder setup here. So let's look first at two channels, A and B. And you get these two channels when you have not just one, but two pairs of this photoemitter and photodetectors looking at the system. So let's say you have one photoemitter detector pair around here and another photoemitter detector pair over here. And if they're set up correctly, they're out of phase by 90 degrees. So that is that every time you see a pulse on this A channel, so let's call this one A and this one B, every time you see a pulse on the A channel, you won't see a pulse at that same time on the B channel. You'll see that pulse on the B channel a little bit shifted, and it'll be shifted by a quarter of the full wavelength of a pulse on and pulse off. And that's why it's 90 degrees out of phase, is because 90 degrees is a quarter of 360. So what happens to allow you to get more useful information when you do a phase quadrature encoder is that there are all of these different states, states 1, 2, 3, and 4 shown here. And in these states you have different combinations of channel A and channel B. So for example, if you're in state 1, you can see that channel A is high, but channel B is low, and that's indicated in this diagram. And then when you get into state 2, both channels are high. So what this series of states allows you to do is it allows you to sense the direction of rotation. If you only had one channel and you started going the other direction, you wouldn't be able to realize it, because you would just see one set of pulses and you would know that something has passed by, but you wouldn't know that it's switched directions. But with two channels, if you go from state 2 to state 1, you know you're rotating backwards. But if you go from state 2 to state 3, then you know you're rotating forwards. So this direction of rotation is a really important feature of doing phase quadrature encoding. The other thing you get for free along with this is really a 4-fold increase in resolution. Rather than just knowing when it's on or when it's off, now you have 4 states that give you a lot more information about what's happening at any particular time. So this is the most common way in which optical encoders are used in both robots and haptic devices. The other sensor I wanted to mention is the potentiometer. The potentiometer is a really cheap and useful way of sensing a position or specifying a position by changing the voltage through what's called a voltage divider. So basically what you do is you attach one pin of the potentiometer to a 5-volt source and you attach the other end to ground. And then the third pin on this potentiometer is an analog input or sensing pin. And basically what's inside the potentiometer is a big resistor, and as you rotate, if you take your hand and you rotate this knob here, it's going to move this pin which is touching the resistor which is inside, and it's going to change its position. And depending on where it's changing its position, you're going to get different amounts of resistance at the top of the circuit and the bottom of the circuit. And this can be shown by this diagram over here. So this now shows a voltage source. It shows there's one resistor here, but it's really divided into two resistors, R1 and R2. And then you can measure at different points. And this just shows that there could also be a load resistance as well. But the main point is that this arrow can be moving back and forth to change the relative values of R1 and R2. And if you know that the source voltage is 5 volts, you can create a circuit equation that will tell you how far along you are on this potentiometer. And it's typically something that you would also need to calibrate if you're going to use a potentiometer as a position sensor and not just some sort of user input. These are examples of a bunch of different potentiometers and what they look like. If you were going to use a potentiometer as a rotation sensor for a haptic device, you would typically use something that has an actual knob on it like this so that you can attach to it. One word of caution on using a potentiometer with a haptic device is that because the way in which it works is by dragging a pin along a physical resistor, it has some inherent friction to it. The optical encoder is non-contact. The magnetoresistive sensor is non-contact. That is, the information is just traveling through free space. There's no physical connection between the thing that's rotating and where the sensor is. And so that means they're nice and low friction and the user won't feel the effect of the sensor. But because the potentiometer has friction, unless you get a very low friction potentiometer, which makes them a little bit more expensive or sometimes a lot more expensive, it might be difficult to integrate a potentiometer to a haptic device and still have the haptic device feel the way you want it to.